In the previous video, we solved this problem by defining our system as broadly as possible, which is what we want to do. Remember, physicists didn't invent gravitational potential energy to make your life miserable. They invented gravitational potential energy to make their lives easier. Most people prefer using it when solving energy conservation problems. So let's take a look at some other definitions of our system and see how that changes our energy equation. Last time, we started with our most basic energy equation, E initial plus the work done by friction plus the work done by external forces is equal to our final mechanical energy. And we said, what is mechanical energy? It could be kinetic, gravitational potential, or spring potential. So we could have any or all of those at the beginning of our problem. We've got the work done by friction, work done by external forces, and we could have kinetic, gravitational potential, or spring potential energy at the end of our problem. And this is the way we defined our system. So this time around, I'm going to change it up a little bit. Let's exclude the spring from our system. So now our system is our mass and the earth. The spring is excluded and the hand is excluded. So let's take a look at how our energy equation changes. Is our object moving at the beginning of the problem? No, it isn't. It's at rest, so it has no kinetic energy. Is it moving at the end? Yes. So we'll have some kinetic energy we have to account for at the end of our problem. Does it go up or down? Does the elevation change? No, it doesn't. So our gravitational potential energy is going to be the same at the beginning and the end. It's going to cancel out. We can just call it zero at both cases. Do we have a spring in our system? No, we don't. So we cannot use spring potential energy. But what do we need? We need work done by the spring. We need to account for it as an external force here. Work done by the spring. We have friction in our system. We have to account for that here. But we also have another external force, right? We have one here, that's the spring reaching in. And we have another one over here, that's the hand reaching in. So I need a second work external from the pulling force. So now when I write this equation out, I've got the work done by friction, which is the friction force, times the distance it's being applied, times the cosine of the angle you get when you put their tails together. That's a cosine of 180. That's our minus sign that we always get with work done by friction. Then I have the work done by the spring. Work done by the spring is going to be plus or minus 1/2 kx squared, the distance the spring stretches or compresses. So this is the difference here. Spring potential energy, like we did in our previous problem, is always positive 1/2 kx squared. Work done by the spring could be positive or negative. So in this case, is the spring doing positive work on our system, or is it doing negative work on our system? Is it causing the mass in our system to increase in speed or decrease in speed? It's causing it to decrease in speed. The mass would be moving much faster if the spring was not there. It's pulling back on the mass as the mass is trying to move to the right. So we need the negative. We also know what x has to be, right? X is the distance that the spring is stretched, which is capital D. Now we need the work done by our pulling force. We know that it's positive. The pulling force is adding energy to our system, to our mass, causing it to move faster. So this is the pulling force times the distance times the cosine of 0 degrees. I'll just leave that out. At the end of my problem, I have kinetic energy. And that's my equation. You'll see if you compare this to the previous video, it ends up being the exact same equation. We just got there taking a different path. If you'd like, we can finish the problem by putting numbers in. We were given some numbers here. Before we do that, we can write our friction force as mu times the normal force, and the normal force in this case is just mg. Our distance is given, and our cosine 180 gives us a minus sign. And now we can plug in the numbers that were given and solve for V final. Here are the numbers that were given. Mu, the mass, is 10 kilograms. G is 9.8 meters per second squared. The distance was 0.7 meters. K is 30 newtons per meter. Our pulling force is 50 newtons. Here I have a kilogram meter per second squared times a meter. So this is a Newton meter. Here I have a Newton meter multiplied by meters squared, so I end up with a Newton meter. And this also Newton meters. We said a Newton was a kilogram meter per second squared. So the meters from here and the meters there gives me a meter squared. And the kilograms cancel. And I get my final velocity is the square root of 13.93 over 5 meters squared over seconds squared, which gives me 2.79 meters per second.